we have seen the expression of kinetic energy. Okay, we have seen that kinetic energy in general can be calculated as half mvg square plus half ig omega square. And we said that in case we know where is the IC, we can use that T is equal half inertia about IC times omega square. Now, this chapter is very similar to the chapter of work and energy. So a lot of formulas are common. So first, if I want to find the work of a constant force, all I have to do is to project the force on the direction of motion. So I have work of the force is F cosine theta S in case F is constant and theta is constant. Now, for the work of the weight, also we have the same formula, but now delta Y is for which point?
G.
For the center of mass, okay? So when I say minus W delta Y, when I have a rigid body, delta Y represents the variation in position of the center of mass, okay? This is the only difference. So I cannot take any point on the body, I should take the center of mass G. And in case I have a spring, I have the same formula for the work of the spring. The work of the spring is half K delta S1 square minus half K delta S2 square. And here in this problem, they gave us first the work done on the spring. So first you can find the work done on the spring, and by principle of action reaction, you can deduce the work done by the spring, which is opposite. Now, the forces that will not work are forces that are perpendicular to motion, okay, or applied at point of zero velocity. For example, if you have rolling without slipping, okay, in case you have rolling without slipping, then the IC will be at the ground level because the ground is fixed and you don't have slipping. So the velocity of this point is zero. Because the velocity of this point is zero, then the friction force which is applied at this point will not do a work. This is why when we have rolling without slipping, we say that the work of friction is zero because it's a static friction, not kinetic friction. So pay attention. When they tell you rolling without slipping, the friction force will not do a work because it's a static friction. Now, what is new here for a rigid body that is not present for a particle is the work of a couple moment, okay? Because for the particle, we only have forces applied on it. Since it's a point, we cannot have a couple. So for a rigid body, we can have couples since forces are applied at different points of the body. And we can say that the couple can be calculated by F times R. So if I have two opposite forces equal in magnitude, they will produce a couple equal to F times R. And as you can see here, the direction of rotation can be found from the right-hand rule. So here you have this couple is rotating in the clockwise direction. Now, in order to derive the expression of the work of a couple, let's consider two opposing forces acting on a body. So each force will produce a work. If you consider the work of this force F, this force F will cause a small displacement dF. And you know that the work of the force is F times dF. Okay? So here, if you look at the figure here, the displacement ds, which is here, the distance from here to here, can be related to the distance from O and the displacement angle d theta. We can replace ds by r over 2 d theta. Therefore, if we do the work of this force and the work of this force, both will be equal to F times r over 2 d theta. So in total, the work is F times r times d theta. And I can replace Fr by moment m. So I can say that the elementary work of a moment couple is m times d theta. So like we have the work of a force is integral F ds, the work of a couple will be integral m d theta. So, and in case my moment is constant, I can take m outside of the integration. I get that the work of m is m times delta t. Now let's take an example. The bar shown has a mass of 10 kilogram and is subjected to a couple moment of 50 Newton meter and a force P equal to 80 Newton, which is always applied perpendicular to the end of the bar. The spring has a non-stretched length of 0.5 meter and remains in the vertical position due to the roller guide at B. Determine the total work done by all the forces acting on the bar when it has rotated downward from theta equals 0 to theta equal to 90 degrees. So here we know the initial position. The initial position of the bar is the horizontal position, okay? And we have rotation. And we want to find the total work done. So first we should look at forces acting on my system. I have force P, okay? Force P is perpendicular to the bar. Because force P is perpendicular to the bar and I am doing rotation, so P is what? What will be the work of P?
مش زيرو.
No.
No.
P is perpendicular
It will be
to motion. P perpendicular
P
to the
times
bar.
distance.
It's a long motion. Why? Because what is just the type of your motion here? You have a circular motion, yes or not?
okay.
You have a circular motion. So this is, if I draw the tangent to my circle, this is the tangent to my circle. It's perpendicular to the bar. Okay? So P is along at any point, because P is perpendicular to AB, which is the radius. Since always it's perpendicular to the radius of rotation, then it's a long motion. So how to find the work of P? I can say that it's integral P ds, okay? But P is constant in magnitude, so I can say that the work is equal to P times delta S, okay? What is delta S? How to calculate the total linear displacement? You know that the S is what? The S is R d theta, yes? The S can be written equal to R d theta because it's a circular motion. R d theta, okay? So we can say that the total, so delta S is equal to R times delta theta. What is delta theta here? I moved from 0 to 90 degrees. So delta theta is pi over 2, okay? So delta S is R times pi over 2. Therefore, I can say that the work of P, so work of P is equal to P times R times pi over 2, okay? Now, what are other forces applied to my system? I have the spring, okay? I have the spring force. And pay attention what they said. They say that we have this spring will remain always in the vertical position because we have the roller guide, okay? So imagine when the bar was horizontal, what was the length of my spring? It was equal to delta L1 was 0.75, okay? And when my bar is at this position, after doing rotation, my spring will remain vertical. It will not be inclined because I have the roller guide here. So the total length of my spring here will be equal to this one. What is the length here now? The new length of my spring is 0.75 plus this part from here to here, which is what?
2 cosine theta.
2 cosine theta, okay? So in a general location, I have 2 cosine theta. In particular, for theta equals to 2 sine theta, not cosine, 2 sine theta. So for theta equal to 90 degrees, when my bar is at this position, what will be the total length of my spring?
2.7.
2.75.
Very good, 2.75, because it's this distance from here to this point, to this one. So this point will go to this position. So I have that the total length becomes 2.75, okay? And they said that the unstretched length is 0.5. So I can say that delta L1 is equal to 0.75 minus 0.5 equals to 0.25, and delta L2 is equal to 2.75 minus 0.5 equals to 2.25. Okay, so I have delta L1, I have delta L2. I can find that the work of the spring is half K delta L1 square minus half K delta L2 square. What are other forces which will produce work? شو بعد فيه؟
الويت.
Weight, very good. Weight is applied at the center of the bar, and we know that the expression of the weight is minus mg. So I have that work of weight equals to minus mg delta y. Delta y of which point? Of point G. Pay attention, okay? So how to find delta y of G? At the initial position, when my bar was at the horizontal level, I can take this as my reference, okay? Here y of G is 0. When I take, so if this is my y coordinate, when I take the vertical position, what will be the position of y of G? G is at the center of the rod, okay? So if the distance is 3, if the total length of the rod is 3, then AG is equal to what? 1.5, okay?
1.5 sine theta.
Yes, so I have minus 1.5. هلا مظبوط. If I want to take any general position, it's minus 1.5 sine theta. But because I am just interested in the vertical position, theta is 90 degrees, so sine theta is 1, and it's minus 1.5. Okay? So here the work will be positive, because delta y is negative, I'm going downward. So the work will be equal to plus mg times 1.5. Since delta y is negative and I already have minus, so this is the work of the weight. Now, شو بعد في؟ بعد في شي work ما انتبهنا له؟
في المومنت.
Yes, the work
في
of the
couple.
moment.
المومنت couple. Okay? الكابل moment شو الwork تبعه؟ What is the formula for the work of a couple?
mg theta.
Yes, it's integral md theta. But because m is constant, so we can say that the work of the moment. كيف بنعرف إذا positive أو negative? I should look if the couple is in the direction of rotation or not. كيف عم تبرم البار؟
بلا.
البار عم تبرم clockwise والmoment is clockwise. So the work of the moment is m times the delta theta, which is pi over 2. Okay? And now I can sum all of work of these forces to get the total work. Okay? الرياكشن at A عندها work. The reaction at the pin here. I have a reaction عندها work شيء.
لا.
لا, why? Because A is fixed. So it cannot
fixed
produce any work. Okay? Any question for this problem? So it's a very simple chapter. Okay. Now, for the principle of work and energy, we can apply it for a system of rigid bodies like we did for a system of particles. So if we have several particles, we can say that sum T1 plus sum of work from 1 to 2 equals to sum T2. Let us consider another example. The 30 kilogram disc shown is pin supported at its center. determine the number of revolutions it must take to attain an angular velocity of 20 radians per second starting from rest. It is acted upon a constant force F, which is applied to a cord wrapped around its periphery, and a constant couple moment of 5 Newton meters. Okay? So here we want to find what is the number of revolution needed to attain an angular velocity of 20 radians per second starting from rest. Okay? So what to do here? We know what is the couple acting on the pulley. We know the force F acting on it. You can solve this problem. We will solve it in two methods. The first method will be a review on what we did in previous chapters, 16 and 17. And the second method is what? Is work and energy. So if you remember, it's very similar to chapter 12, 13, and 14. In some problems, you can solve a problem using chapter 14, using principle of work and energy. And you can use the same problem, you can solve it in chapter 13 and 12 by using kinetics and kinematics of the part. This is similar here, okay? So let's say here we want to apply work and energy. If you want to apply work and energy, what will be our equation? We have that T1, which is the initial kinetic energy, plus what are the forces and couples doing work here? We have the work of F, plus we have the work of the couple moment M. The weight will do a work here?
No,
No. Why?
because it starts from the center of mass, or
Yes,
which is
because
fixed
the
point.
center of mass here, which is fixed, so the weight will not do any work here. Okay, so we have the work of force F, we have the work of couple equals to T2. Okay, now since it's initially starting from rest, then T1 is 0, so we can drop T1. We don't have T1. Now, what is the work of F? What is the work of F? Who can tell me? You have rolling without slipping. Because you have
Times the
rolling
distance
without
is
slipping.
RD factor.
Yes,
F
the
times delta
displacement
S.
of the cable delta S. So this is the displacement of the cable delta S. So delta S can be related to what? If you want, we can say ds is equal to radius r times d theta. Okay, so we can say that delta S is equal to r times delta theta. So we can say that the work of F is equal to F, because it's constant. I can take it outside of the integration. It's F times R times delta theta. And what is delta theta here? It's unknown. I want to calculate delta theta. Okay? Plus, what is the work of the couple?
Moment times delta.
Yes, very good. Moment M times delta theta. Okay? So here my only unknown is delta theta equals to, now, what will be the final kinetic energy? What is the expression of the kinetic energy here? You have rotation about a fixed point. So what do you use?
Half
I theta prime squared.
Very good. So half I inertia about O, okay, times omega final square. Okay. Now the inertia about O, how to calculate it? It's a disk. When you have a disk, the inertia
Half
about
m r
O
squared.
is half m r squared. Okay. You can get the value of this inertia. Now, the only unknown in this equation is delta theta. You get delta theta. Now, once you have delta theta, how you can calculate the number of revolutions? I want you to find the number of...
نعمل d theta over 2 pi.
Very good. Because each revolution is 2 pi. Okay? So we have that delta theta is equal to the number of revolution and times 2 pi. Okay, so to calculate n, the number of revolution, we divide delta theta by 2 pi. Let us try to do together this problem without using work and energy. If you want to use what you learned in chapter 16 and 17, what will you do? So first, I can find what? Who can tell me? When you want to find a certain velocity, angular velocity, and relate it to number of revolution, okay, you can find what? You can find alpha, because if you know alpha, you integrate, you get the expression of velocities, and you integrate, you get the expression of theta. Okay, so the other method to solve this problem is to use chapter 17 and 16. So first, if I use chapter 17, I will do sum of moment about O equals to IO alpha, because O is a fixed point. Okay, if I do sum of moment about O, what do I get? I get F. I will take the clockwise direction as positive. F times R plus moment M, okay, equals to IO alpha. My only unknown is alpha. I get alpha, and alpha here is constant because M is constant and F is constant. Because alpha is constant, then I can apply the relation of constant angular acceleration. So I can say, if I don't want to involve time here, no need to involve time, because if I involve time, I should do two steps. I should integrate first to find angular velocity, then integrate to find theta. However, because here I have final velocity, initial velocity, and I have alpha, I can use what? I can say omega final squared minus omega initial, which is 0, because it's starting from rest, square, equals to 2 alpha times delta theta. Okay? And in this way, I can calculate delta theta. I will obtain the same result. Clear? So as you can see, we can use combination of chapter 17 and 16 to solve this problem, or we can use work and energy to solve. Any
بس
question?
سؤال
No.
ما فهمت ليه الورك تبع اف هي اف تايمز ار تايمز دلتا فتا.
لأنه الورك تبع اف انجلو هي شو؟ مش هي اف تايمز دلتا اس displacement.
بلا
طيب what is delta s? How you calculate delta s? مش دي اس هي ار دي theta. Okay.
بلا
يعني what is delta s? It's r delta theta.
اوكي
Any other question? Okay. Another problem. The 700 kilogram pipe is equally suspended from the two times of the forklift. If it's undergoing a swinging motion such that when theta equal to 30 degrees, it is momentarily at rest, determine the normal and frictional forces acting on each bar which are needed to support the pipe at the instant theta equals to 0. Measurement of the pipe and the suspender are shown here. So in this problem, it's like a pendulum. At the initial position, you have a certain angle theta and you leave it. When you leave it, it will swing around the vertical position. What they want us to find is the reaction, okay, the normal and frictional reaction at O when it is in the vertical position, okay? So first, what should I do? First, you know that to calculate the reactions N and F, you need to find AN. And to find AN, you need to calculate V. Why you need to find AN? Because at the vertical position, when you take the vertical position, what are forces acting on your system? At the vertical position, you have the weight. So here, let's put it here. You have this, and you have here a circle. Okay. So I have this is my system, and this is the bar. So at the vertical position, this is my system. Okay? I have, as forces applied on it, I have the weight, and I have the reaction at O. Okay? So they asked for the normal and frictional forces. So let's assume I want to calculate. So this is, let's say this is F, and this is N. You can see that W and the N are along what? Along UN, and the friction force is along UT. Okay? So this is F, this is N. Okay? And I have here UN UT will be like this. So I will draw UN UT at point G, because G is the center of mass. So this is UT, and this is UN. Okay, so this is UT, and this is UN. Okay, now to be able to find these forces, we want to apply sum of T equals MAT, and sum of N equals to MAN. Okay, so to start with, we will find, to find normal force, we need to find velocity. Why? Because we know that sum of N is equal to, so sum of Fn is equal to MAN, and AN is equal to V square over R. Okay, so it's mv square over the radius of rotation. Here the radius of rotation is what? Is 0.4. Okay, because look, R is the radius of rotation of G about O, and as you can see in the figure, the radius of G about O is equal to 0.4 meters. Okay, now sum of N is equal to N minus W, N minus W, so equals to mv square over R. So to find N, we should calculate V. To calculate V, we can use what? We can use the principle of work and energy between the inclined position, which is corresponding to an angle of 30 degrees, and the vertical position here. Okay, so if we apply work and energy, what is the only force doing work here?
Weight.
Weight, very good. Okay, so and what is the work of the weight? It's minus mg delta y of point G. What is delta y of point G here? How you get delta y of G? At the initial position, what was y of G? So if I take both are negative, if I take y upward, both are negative. Okay, but y at the initial position, yg is what? It's minus 0.4 cosine 30. While at the vertical position is equal to what?
0.4.
Minus 0.4. Okay, so you can calculate the work of the weight, and of course it will be positive because delta y is negative and you have minus mg delta y. So we can say that the work of the weight is equal to T2. Okay, because T1 is 0 since it's starting from rest. Now how to calculate T2 here? Here you have two possibilities to solve this problem. Okay, because when you have here, you have rotation about fixed point. So you can say or T2 equals half mvg square plus half ig omega square, or you can say that because I have rotation about fixed point, what is the fixed point? Is O. Okay, because it's about rotating about O, I can write that it's equal to half IO equals to half IO, okay, times omega square times omega 2 square. And to find IO, what should we do? We use the parallel axis there. Okay, so both are right. So or you can use the general expression, which is half mvg square at state 2 plus half ig omega at state 2 square, or you can use the parallel axis theorem to find IO and then apply half IO omega 2 square. Okay, but in both cases you need to relate here, and if you use this case, you need to relate Vg and omega 2, because here you have two unknowns. You want to reduce it to one unknown. So how to relate Vg2 to omega 2? If you go back to this figure, G is rotating about a fixed point O. So what is Vg2? So at any instant, V of G should be equal to what? To 0.4 omega. So Vg at state 2 will be equal to 0.4 times omega 2. Okay? And if you replace here by Vg by 0.4 omega 2, you can have only one unknown, which is omega 2. And this is equivalent to the parallel axis theorem. You know why? Because if you take omega 2 square into factor, what do you get? You get Ig plus m times 0.4 square. And what is Ig times m plus 0.4 square? Look, what is IO? What is IO? IO is equal to Ig plus m times the distance between O and G square. Okay, so if you use this relation, you will go back to the parallel axis theorem, because if you take into factor half omega square, you will have inside Ig plus md square, which is IO. Okay, so both methods are equivalent. And now your only unknown is omega 2. So you apply the principle of work and energy, you get the value of omega 2. Okay, once you get the value of omega 2, now to find the normal force, the normal and the frictional force, you will apply, for the normal reaction, you will apply sum of n. And for the tangential, for ut, you will say that sum of t equals to MAT. But what is MAT? Do you know what is MAT? At the vertical position? What is MAT at the vertical position, guys? Who can tell me? So for n, it's fine. For ft, how to find ft? We said that sum of t equals MAT. But how to get AT? In rotation about a fixed point, what is AT? AT is alpha times radius times r. And here r is the distance from G to O, so times OG. So it's equal to, AT is equal to 0.4 alpha. Okay? And now, because to find AT, we should find alpha. To calculate alpha, what should we do? We can do sum of moment about O equals IO alpha, or sum of moments about G. Both are right. Okay? So, but if we do sum of moments about O equals IO alpha, we directly get alpha 0. Why? Because look, all forces are not doing any moment about O, and T and Ft are not doing a moment, and the weight also is not doing a moment. So sum of moments about O is equal to IO alpha. And because it's 0, then alpha is 0. Okay? And because alpha is 0, AT will be 0, and sum of T will be 0. So force Ft will be 0. Question on this? Any question? Okay. Now, here also for a rigid body, we can apply the conservation of energy, okay? If all forces are conservative. So if you have, for example, a rigid body only subjected to conservative forces as weight and spring, then you can apply the conservation of mechanical energy. And you can define for gravitational potential energy, it's like a particle, but the only difference is that you take y of g. So Vg is W times y of the center of mass. And for a spring, it's the same formula. The elastic potential energy is half K delta S squared. So in case you have only conservative force, you can apply the principle of conservation of energy, which is T1 plus V1 equals T2 plus V2. And if not, if you have non-conservative force, you can write your theorem of work and energy in another form, which is T1 plus V1 plus sum of non-conservative forces equals to T2 plus V2. Let us do an example on this. The 10 kilogram. Look, time will be over now. So next session we will start to do review for chapter 15, and you continue chapter 18 after your exam. Okay? Yeah, I will start a new session.